All right, we're gonna start. So settle down.
One can equal to 0. It's inconsistent as well, but
So this class is not for sure.
Let's run through the quiz.
This class is for class.
Okay, so it said to solve the following two systems, or if you can't solve them, write inconsistent. So one part A. I'm just going to write down the augmented form so you can see the system here. So hopefully you got to the part where the augmented form was this. And 0, 2, minus 2, 1. So it should look something like that. So it's 1 minus 1, 2, 3, 1, 2 minus 1 minus 3, and 0, 2 minus 2. Okay? So what did you do? First step.
Subtracted the first row with the second row.
Okay, so you can take like row 1 minus row 2.
Right.
So row 1 I would just kind of leave at first because it already had the pivot here. And I want to kill that guy, so I did this minus this, 0, this minus this, minus 3, this minus this, positive 3, this minus this, 6. Okay? And then what? You can probably copy that again if you want.
Could you divide it by 3?
We could do row 2 divided by minus 3. So again, I'd leave this guy for the time being, divide this by minus 3. I would get 1 here, minus 1, and minus 2. And notice that these guys I can use to kill that guy. So let's say that row that I just created, row 2 over minus 3, I'm going to multiply that by 2 and subtract row 3. So this times 2 minus that, 0. This times 2 minus that, 0. This times 2 minus that, 0. This times 2 minus that. Well, this times 2 minus that. And that would give me what? Minus 5. Right?
Yeah.
And so now what does that mean? That row here means it's inconsistent. So part 1a was inconsistent because now I have an equation that says 0x plus 0y plus 0z equals minus 5. That makes no sense. Lightning strikes. 1b. Another system, so write down the augmented form. 2, 1, 2, 4, minus 1, 2, minus 2, minus 3. So 1, 0, 1, 2, 2, 1, 2, 4, minus 1, 2, minus 2, minus 3. Okay, so that was the guy. And so what do we do here? I'd probably leave row 1 alone for the time being because it already has that 1 there. And I'd probably take something like 2 row 1 minus row 2. Right? So 2 times this minus that, 0. 2 times this minus that, minus 1. 2 times this minus that, 0. 2 times this minus that, 0. And then here, to kill a 0 here, I'd probably just add these 2 rows. So I'll just take row 1 plus row 3. This plus this, 0. This plus this, 2. This plus this, minus 1. This plus this, minus 1. What else could we do here? Leave this guy for a second. This guy I can actually just change it to that by just taking row 2 times minus 1. Third row I would change something like 2 row 2 plus row 3. So 2 times this plus that, 0. 2 times this plus that, 0. 2 times this plus that, minus 1. 2 times this plus that, minus 1. Technically, you could stop here. We're already sort of seeing what the numbers are going to end up, but let's just go one more step and take this to RREF. We can just add these 2 rows to kill that one up here. So I would take row 1 plus row 3. 1, 0, 0, 1. This guy's just 0, 1, 0, 0. This guy can just take row 3 times minus 1. Here I just recopied row 2, so that's 0, 0, 1, 1. And so this would mean that my x, y, z equals 1, 0, 1. So this one had a solution, and it was 1, 0, 1 is the vector. The 1a was inconsistent.
Professor, you don't get partial.
Not on quizzes, no. On tests you get partial credit, but not on quizzes. Let's go to 2. So 2 says we had a system in the variables w, x, y, z, and we found the reduced or echelon form. So the reduced or echelon form of some system in variables w, x, y, z is, and that it's given to you. So the work was already done, and this is the reduced or echelon form. 1, 0, 0, 2, 1. 0, 0, 1, 2, 3. Right, so that was the reduced or echelon form of a system, and they told you that the variables were w, x, y, z, so that means that the first column was a w, the second column is x, y, z. So how do we deal with that situation? Yeah.
X and Z would be free variables.
X and Z are free variables. We have 2 pivots here. There's one in the W column, there's one in the Y column. There are no pivots in the X and Z column, so they're free variables. We will not have an equation where we can solve for them. So we simply set them to be whatever. We can say set X equals A, Y equals Z equals Z equals B. Right? But you can use any letters here, that's fine. S and T, R and Q. You can use any variables to represent these except the variables that are here. You could also set x equal itself and z equal itself, that's also fine, but you can't set them equal to w or y, for instance. So that would be that. Then you go to row 2 to figure out the other people. Row 2 says y plus 2z is equal to 3, but my z is b. So this means that my y is equal to 3 minus 2b. Move up to row 1. Row 1 tells me that w plus 2z is equal to 1, but remember my z is b. So this means that my w is going to be 1 minus 2b. Or not to be. Okay, so now we can actually write down the solution. W, x, y, z equals, the w is 1 minus 2b. The x is a. The y is 3 minus 2b. And my z is b. So this system has 2 free variables. At this point, I would give you the credit if you have something similar to this where your A and B can literally be any other 2 letters. But I would prefer in general that you break them up. So break it up in the constant vector that doesn't have any letters on it. So that would be the 1, 0, 3, 0. A only appears 1 time in the second column. B would be minus 2, 0, minus 2, 1. So this answer will work at this point. I would have preferred if you wrote the answer as this, because in the future, these 2 vectors here are going to be very important for us. So it's nice for us to flesh them out. They're going to help form what we call a basis. So that was problem 2. Well, the bonus we'll save. We're going to talk about the determinant today. But for the actual quiz, that was what he said. The goal is by the end of today, you'll know how to do some parts of the bonus. We're still in 1.2. I just want to kind of wrap things up nicely and summarize some things. And we can talk a little bit about homogeneous systems. So 1.2 continued. Recall the system is inconsistent if it has no solution. That means there's no set of variables that we can plug into that system to make all the equations true at the same time. We can identify inconsistent systems. By their row echelon form or their reduced row echelon form. By looking for a row like, so the row would have to look like there are zeros everywhere, but on the other side of the equation, there's a number where that number is not zero. This gives you an impossible condition, right? So if you want to figure out if a system is inconsistent or not, meaning it has no solution, all you do is find the reducer echelon form or the row echelon form. As long as you can reduce it to get a row that looks like this, it means that there's no solution to that system. Right? So, and we call that system inconsistent. So I think that's where we ended up last time. A system is called consistent if it has some solution. Now let's actually qualify that a little bit, because last time we did a bunch of examples, and I told you guys that there are only 3 situations, so now I'm going to actually give you a theorem that says just that. So the varieties of solutions of linear systems. So in terms of solutions, there are 3 situations you can find yourself in when you do a linear system. Let's do one definition first before I mention the theorem. I'm going to define a new word for you called the rank. The rank of A, which you can denote by rank A, is the number of pivots in its REF or RREF. That's it. You just count the number of pivots once you reduce it. That number is going to be we call that the rank of the matrix. This is equal, it's the same thing, you can think of it in two different ways, whatever you're counting, to the number of non-zero rows in its REF or RREF. Because of course if there's a row of zeros, there's no pivots, and if there's a non-zero row, the first number in it, we want to make it be a 1 and it will be called a pivot. So we can talk about the rank of a matrix. This is just the number of pivots that are there once we reduce it to row echelon form or reducer echelon form. So, example, I said A equals 1, 0, 0, 3, 4, 0, 0, 0, 0, then the rank of A is what? 2. Right? So the rank is just a real number, just counting the number of pivots. There are 2 pivots in this matrix, here and here, so the rank is 2. That's it. Okay. Here's an important theorem about the solutions. Given an n by m system of linear equations, ax equals b, so we can write it in the matrix form. There are exactly 3 possibilities for its solution set. One possibility is that the system will have no solution. There will be no set of variables in this linear system. There will be no vector x that will solve this equation. So there will be no set of variables or set of coordinates that you can plug into that linear system to solve all equations at the same time. This is called an inconsistent system. So this means inconsistent system. So that's one possibility. The other possibility is the system has a unique solution. That's the other possibility. The third possibility is the system will have infinitely many solutions. And so these two situations here, we have a consistent system. So a consistent system means it will either have one solution or infinitely many. There is no in between. You can't solve a system and have 3 solutions. It's not going to happen. You'll have none, exactly 1, or an infinite amount. It's a very important theorem, but we're not going to spend too much time on it. In fact, I'm not even going to prove it in detail, just give you like a little proof outline here. So you might have to be careful with the language, and I'll do some hand waving, but it's essentially a proof by cases. So given AX equals B, augment the system form. Now here you have, there are two cases. One, it has no solution. Or two, it has some solution. Basically, once you put it in reducer or echelon form, you'll either get a row that looks like a bunch of zeros leading up to a non-zero number, or not. There are only really two. You either can have that or you cannot have that. So if you have that, you have no solution. Or if you don't have that, you have some solution. So now, this will split into two cases. So these are two subcases.
Oh, question.
Yes?
How come the third outcome, where there's infinitely many solutions, is a consistent system? Is it because there's no contradictions in logic?
Well, I'm going to tell you why right now. So in this case, we have no solution. In this case, we have some solution. So let's prove that we'll either have exactly one solution or we'll have infinitely many. There are two subcases. Either the rank of our coefficient matrix will be equal to m, or the rank of the coefficient matrix will be less than m. Basically what I'm saying is either there's a pivot in every column. It's a mathematical way of saying there's a pivot in every column, or there's not a pivot in every column. Right? What happens if there's a pivot in every column? You'll be able to say this variable equals that, this variable equals that, this variable equals that, this variable equals that. For each variable. And so this would give you a unique solution. If there's not a pivot in every column, what happens? Columns without pivots invoke free variables. So any column that doesn't have a pivot, the variable that controls that column gets to be whatever it wants. So this means you have infinitely many choices. Leading to an infinite number of solutions. So not a strict proof, you really have to write this down and make it look nice and really be detailed with it. But that's basically the idea. Given any system, we can augment it, we can put it in reducer or echelon form. Either we get a bad row or we don't get a bad row. If we get a bad row, that means we have no solution, that's situation one. If we don't get a bad row, there are two possibilities. Either every column has a pivot or every column doesn't have a pivot. If every column has a pivot, each variable has a unique number associated with it. If every column does not have a pivot, then the variables without pivots get to be whatever they want. They get to be free variables. And so you have infinitely many choices for those variables, hence you get infinitely many solutions for the system. So there are really only three possible situations for any linear system. And a linear system will never have any other set of possibilities in terms of its solutions. So that's nice. And we use that fact elsewhere, but we're not going to get into it right now. We're just going to run with that. Next, I want to talk about what we call a homogeneous system. Those are very important. So let's talk about homogeneous systems. So in a system AX equals B, if your B vector is the 0 vector, we call the system homogeneous. So that's our definition. So a homogeneous system is a system of the form AX equals 0. So any set of systems of equations where on the right side there's just a bunch of zeros, we want to solve for this guy equals 0. So we want to find all the vectors that we can plug into our function with that output 0. We call such a system homogeneous. One important thing about homogeneous systems, besides the fact that they have very important applications, this is how we'll find later on. You'll see, like way down in chapter 4, the solution to this system form what we call a null space. That'll be very important for the functions that we're considering. But for now, just understand that this is a possibility. You can have a bunch of zeros here, and it's called a homogeneous system in that case. And homogeneous systems are always consistent. Namely, if I take the input to be the 0 vector also, it will solve the system. So plug in 0 for all the variables, and the output will be 0. That's definitely a solution. It might have other solutions. But that solution, that's the easy, brain-dead one that you don't have to think about. You definitely know it's there. So it's called the trivial solution. X equals 0 is called the trivial solution. It's kind of the one you don't have to think about. It's very trivial. Obviously, that's a solution. It is possible to have others for certain systems. In fact, by the previous theorem, if it doesn't only have the trivial solution, it has infinitely many solutions. So that's a fact about a homogeneous system. It just means that the outputs are always 0, and there's literally always a solution. Literally plugging in the 0 vector for the input will be a solution. So in other words, a homogeneous system always has either one solution or infinitely many.
So it can never be inconsistent.
So it'll never be inconsistent in outputs. Because remember in inconsistent, we have something that looks like this, right? That guy is always going to be a 0. So you'll never end up in a situation where you have a bunch of zeros giving you a non-zero number, because on the right side you always have zeros. Later on, we'll actually use this to talk about certain vector fields and linear transformations on those fields. The solution to this actually can tell you a lot about the vector field that you're studying and the function that you're putting on it. in terms of, for example, whether the function is one-to-one or not, and you know, that's kind of things. You can study that by looking at homogeneous systems. So they have a lot of applications in their own right, but right now I want you to know the definition and know the fact that they're always consistent. Not covering as much as I wanted to, but let's be thorough here. Wanted to summarize. If you're very good at solving systems, you probably don't have to write this down, but to solve AX equals B. It's one of the main takeaways from this section, and it's going to be very useful for us to be able to solve systems. One, augment the system. Two, find its REF or RREF. Okay. Now that part is where all the work comes in. You have to be very efficient. First you have to know what these forms look like, and then you have to get to them as quick as possible to avoid any errors or redundancies or mistakes, or just, in general, just taking a lot longer to do it than normal. And as I said, by far the most efficient way I found by hand to do it is just start at the top left pivot, the top leftmost pivot that you can possibly get, immediately start killing all the zeros below them, and then keep successively moving down to lower pivots and doing this. And if you want to go to the RREF, then you start killing the zeros above. And you just do operations that can get you that in that state as quick as possible. I would also recommend that you avoid fractions until perhaps the very last step. So that might be, you might end up in a situation where to get a pivot in a row, you have to divide by a number, but you'd probably just hold off on dividing just to avoid getting fractions elsewhere in the row. So 3. A. If you get a row like, again, 0, bunch of zeros, and you have a number here that's not 0, then the system has no solution. So you just write it's inconsistent. 3. If system is consistent, the first thing you're going to want to do is identify the pivots. So once you get to RREF, there are 2 possibilities. Either you get a row that makes the system is inconsistent, or you don't. If it's inconsistent, there's no solution. If it is consistent, identify your pivots. I mean, you can draw a little circle around them, just make them stand out. For each column that does not have a pivot, its variable becomes a free variable. Set it equal to a parameter. 5. From the bottom row up, create equations from each row. And substitute values from lower rows to higher ones. To solve for each derivative. Doing that, you can solve any linear system in a sort of algorithmic, systematic way. And really, the most of the work happens here. So 2 by 2, all the methods we learned in algebra class, sure, they're still valid. You can use elimination or substitution or whatever. But the bigger your systems get, the more annoying that process gets. It's much more efficient to just throw all the coefficients in a big matrix and just do row operations until you break it down. This eraser is not working well. That ends 1.2. Probably a 5-star. Write solutions as column vectors. Separate the parameters. That'll be important later. You'll see why. So you might as well just practice doing it now. So this is the summary of how we can solve a linear system. And we know all the possibilities. And next, what I want to do is talk about the determinant. So actually jump into 2.1. Where we're going to talk about the determinant. Any questions before we move on? Or are we okay? Yeah.
So in some cases, can we have a fraction in the augmented form?
Yeah, it's possible to have a fraction. Sure. Again, I would avoid fractions in general. So if you put it in augmented form and they're already fractions, I just multiply by the LCD to kill all the fractions and then continue with the process. When you're doing it by hand, you have to do things like that. If you're plugging something into a computer, the computer won't care, but you're going to be doing things by hand. It's much better to avoid fractions, if at all possible. Until perhaps the very last step, they can come in. So in the very last step, to make sure your pivots are 1s in front, you can divide on the last step. But until then, just leave it. Okay. So in lecture 00, we saw, this is way back, given a matrix A, B, C, D, the expression AD minus BC gave the signed volume of the parallelogram. Created by the row vectors. Sign means it can take a plus or minus value, but the absolute value of it is going to be the volume of the area of the parallelogram. Volume here, I mean in general, because I want to talk about higher dimensions. Technically here, with this in 2 dimensions, it was area. It's just a measure of how much space you want to take up. So this was area in 2D, but when you go to higher dimensions, you call it volume, the amount of space something takes up. Okay. So, in fact, we defined, because that was just, it seems like such an important expression, it has a very nice geometrical interpretation. So we defined the determinant of A. It has 2 notations, denoted I can write it as det parentheses a, or I can put absolute bars around it, a, by the determinant of a, b, c, d equals bar a, b, c, d equals, you cross multiply these guys. So this times this, AD, minus this times that, BC. Right, so you kind of do that crisscross thing. And it turns out that that was actually a shortcut to finding the volume or the area of the parallelogram spanned by the row vectors. Okay. So that was sort of nice, so we decided to kind of try to figure that out in general. What if we go to a 3x3 matrix, or a 4x4 matrix, or a 5x5 matrix, or any square size matrix? How do we find the volume of its the parallelepiped it forms in n dimensions?
You breaking it down to smaller matrices?
Yeah, that's what the process is going to be. There are actually many processes for finding this value. They're all just sort of based on algorithms. So what happens is you sit down for a while and you compute the volumes of a bunch of these, and then you see a pattern in the expressions that you're getting, and then you just come up with an algorithm that will fit that pattern. And that's kind of how these guys are computed. So the pattern for the 2x2, this is called the 2x2 matrix, is just you cross multiply this minus the cross multiplication of that, and it gets a little bit more elaborate for larger size matrices. But that was that. Another place this expression shows up before we is when you guessed it, solving systems. So it turns out that that expression is actually important for solving systems as well. In the following way. Suppose we have a system of equations ax plus by cx plus dy equals ef. Right? Notice here that the coefficient matrix is just that. Note. A equals A, B, C, D is the coefficient matrix. Okay. So let's actually solve this the old-fashioned way. Let's actually do like a sort of elimination to kind of solve for the x and the y. So I'm going to name these equations, call this equation 1, call that equation 2. And here's what I'm going to do. I'm going to want to let's eliminate y to solve for x. Right? So I want these two expressions to be kind of the same. So what I would do is I would multiply the first equation by d so that this is this, I get a factor of d. So I get a dx plus b dy equals de. This is equation 1 times d. And I'm going to multiply this equation by, say, minus b so that I can get the opposite there. So multiply this by minus b. And that would give me BD here. That would give me minus BF. That's equation 2 multiplied by minus B. And now let's add these two equations. Here I would get AD minus BC times x. These guys would cancel. Here I would have DE minus BF. And so I can solve for my x. And my x would be equal to DE minus BF divided by AD minus BC. Now there's that expression again, that AD minus BC showing up. And you'll notice that the top expression is a similar expression. I'll flush that out in a little bit. What if you wanted to eliminate the x? So again, I'll kind of multiply by convenient numbers to kind of cancel these. And of course, we're kind of assuming that we can divide by this at this point, like there is some solution. It's possible that this guy is 0, and we have to deal with that case separately. But suppose now I want to eliminate the x, so I want to make these two guys the same, right? So how would I do that? I can multiply this guy by a and that guy by minus c. Let's do that. So by minus ac x minus bcy equals minus ec. It's equation 1 times minus c. And I multiply this by a acx plus aby and af. This is equation 2 multiplied by a. Now I add these two. These guys would die. Here I would have AD minus BC y equals AF minus EC. And so my y would be equal to AF minus EC over AD minus BC. So to solve this 2 by 2 system, I can solve it by getting these fractions. Notice that the denominator of these fractions is a familiar expression. It turns out to be the volume of the parallelogram form spanned by the row vectors. Very interesting that this guy showed up again. Now, note the following. Yeah, I'm not going to be able to tell you how to find determinants. We're running out of time. So that'll be for next time. But know the following. That we know that AB, CD, this is equal to AD minus BC. Okay. It turns out we can find similar expressions to express the numerators. There's another kind of matrix that I can form. Here's how I'm going to form it. Look at it if I take the solution column and replace the x's with it. That means I put EF here and then leave that as BD. And I do the same operation on that new matrix. That would give me ED minus BF. That turns out to be the numerator of the x. Also, you can notice that if I took this column and replaced the y's, that would give me ACEF. And if I do that same operation, I would get AF minus EC, which turns out to be the numerator of the y value. Okay? In other words, if the system ax plus by equals e, cx plus dy equals f has a unique solution, right? Meaning these give me numbers, right? So I'm not dividing by 0 or anything crazy. It is given by x would be the determinant of EFBD divided by ABCD, and my y would be the determinant ACEF divided by ABCD. If this guy, AD minus BC, is not equal to 0. This, by the way, is a very important theorem. It's called Cramer's rule. This is Cramer's rule for 2x2 systems. In fact, we can say it much more generally. So I'll state the general version of Cramer's rule, and then we'll stop there. We probably won't apply it right away because I want to tell you how to compute determinants next time, but we will use it eventually. And I will ask you to use it on a test. So You can start by memorizing the rule, and then we'll learn how to actually apply it next class. So that expression, especially for the 2x2 determinant, it shows up all the time. It's no different actually for larger determinants. So given a square system, AX equals B, this means the coefficient matrix is a square matrix. Then set D equals the determinant of A, and set dxi. So let's say the variables here are x1, x2, all the way up to xn. dxi is going to be the determinant of axi, where this guy is defined to be the xith column in A is replaced with B. Right, so if I take that constant matrix and I replace the column for a specific variable, I get a new matrix and I take the determinant of that matrix, then it turns out I can talk about the solution. Following code. One, if D is not equal to 0, the system will have a unique solution. In fact, we know a formula for it. It will be given by the variable xi will be the determinant of xi divided by the determinant here. And as long as D is not 0, we can do that. We can do this division. So that's one situation. If there is a unique solution, that's how we'll find it. There's other cases. 2. If D is 0 and all the dxi's are 0, then there are infinitely many solutions. Third case, if D is equal to 0 and at least one of the dxi's not equal 0, the system is inconsistent. And I didn't leave space for the title, but this is Kramer's rules. For n by n systems of equations. So that little thing I showed you with the 2x2 system actually works in general. At the moment, we don't know how to actually compute D's for things that are bigger than a 2x2. That I'll show you next time. But at the moment we compute it, this theorem actually gives us the power to solve systems in a relatively easy way using determinants. So this is one use of determinants, is solving systems. So you can avoid using row reduction and use determinants to solve systems as well. And we'll talk about that next time. Let you guys go. Determinants are connected to inverses, but inverses is in another section, another chapter. So
-1 doesn't represent inverse? Like,
if I write a to the -1 power, yes, it represents inverse. Yeah, that's what it is. But we didn't do that yet.
The inverse in the bonus, was that like symmetrical matrices?
No, there's a formula. In the bonus, there was a 2x2.
It's like a 1/.
Yeah, it says if A was a 2x2, like A, B, C, D, then A inverse, that's just like A. It's 1 over the determinant times, it's 1 over AB minus BC times. You switch these two numbers, D and A, and then you change the sign of the other two. So whatever those numbers were, you can just plug into this formula. So, but we'll talk about that later. I'll see you guys on Thursday.